Lesson 1.4, Building Functions from Functions. In this lesson, we're going to add, subtract, multiply, divide two functions together. We're going to take the compositions of two functions, and then we're also going to talk about implicitly defined functions. We're not necessarily going to go too deep into that, just give you a basic understanding. That way, those of you that take calculus have a background of what implicit functions are. So first, we're going to talk about the sum, difference, product, and quotient of two functions. Let f and g be two functions with intersecting domains. Then all values of x in the intersection, these algebraic combinations are going to be true. Okay, so what you need to write down is the sum, difference, product, and quotient. Meaning, if we have two functions f and g, we can add those two functions together to get a function. We can subtract those, multiply, and divide as long as the function that's in the denominator is not equal to 0. Okay, so we're going to look at where the domains are the same, and then use that new domain in order to find all of these different combinations for the functions. So the first example, we're going to go through finding all these different combinations. Let f of x be x cubed and g of x equal the square root of x plus 1. First of all, we need to find the domains for f of x and g of x. The domain for f of x, if that's f of x equals x cubed is just a polynomial, so we know the domain is all real numbers, negative infinity to infinity. If we're looking at g of x, trying to find that domain, well, we have a radical with an even index, so we know the values underneath the radical must be greater than or equal to 0. So if we take x plus 1 and set that so it's greater than or equal to 0, solve for x, we get x must be greater than or equal to negative 1. So our domain is going to include negative 1 and go to infinity. So now that we have the domain for f of x and the domain for g of x, when we find all these combinations, we have to have the intersecting domain for both functions. So the x values that are included in each of the domains for f of x and g of x. So if we look, negative infinity to infinity, there's no restrictions in f of x. So we look at g of x, we have some restrictions. We can't have any x values less than negative 1. So where these two domain intervals overlap is going to be from negative 1 to infinity. So now when we look for the sum, difference, product, and quotient, we have to look at our new domain. Now looking at part A, we want to find the sum of f and g. So we're taking f of x plus g of x, which is going to be really straightforward. F of x is x cubed, so we have x cubed plus g of x is the square root of x plus 1. So we simply have to add those together. And now the domain for these, as we said before, the intersecting domain, negative 1 to infinity. Part B, we want to find the difference. So we take f of x minus g of x. Very similar, we have x cubed, and then minus our g of x function, which is the square root of x plus 1. Our domain is going to be the same, negative 1 included to infinity. Part C, we want to find the product, so we take f of x times g of x, gets us x cubed times the square root of x plus 1. Domain, once again, negative 1 included to infinity. Now part D, we have the quotients. We're taking f of x divided by g of x, x cubed divided by the square root of x plus 1. Our domain for this part is going to be a little different because now we have a fraction. We have to be concerned with what value makes the denominator 0. In this case, negative 1, if we put that in for x, negative 1 plus 1 is 0. The square root of 0 is 0. So we would have 0 in the denominator. So the only thing that changes in our domain is that we now cannot include negative 1. So we have a parenthesis, meaning negative 1 is excluded from our domain, and then all other x values greater than negative 1 will work. Okay, so when going through these problems, first look at f of x, find the domain, g of x, find the domain. Looking at both those domains, we have to find out where those x values intersect. Go through, add, subtract, multiply, and divide those two functions. The domain for many of them is going to be the same. The one where you have to be concerned with the most is when we have the quotient. Okay, f of x divided by g of x. Next, we're going to discuss the composition of functions. Okay, we've talked about these in the past, Fogg and Goff. So let f and g be two functions such that the domain of f intersects with the range of g. The composition f of g, denoted by, this is where we say Fogg, f of g, is defined by the following rule. Okay, we're going to use the notation on the right because I think it's easier to understand what's going on. What this notation is saying is we're starting with our f of x function. Everywhere we have an x in that f of x function, we're replacing it with g of x. Okay, so our g of x function is becoming the domain of our f of x function. Remember, we could do this the other way where we have Goff, g of f of x. And so in this case, we would start with our g of x function. Everywhere there's an x, we would replace it with f of x. F of x is becoming the domain of our g of x function. In the next example, let f of x equal 2 to the x and g of x equal the square root of x plus 1. So we want to find in part A, Fogg, f of g of x, and in part B, Goff, g of f of x. First, we're going to look at the domain for f of x and g of x. We're looking at f of x, the domain. We have 2 to the x, an exponential function. We can put any real number in for x and get a y value in return. So our domain is negative infinity to infinity. Now if we look at g of x, domain, this is the same function we worked with earlier. We have a radical with an even index, so we have to be concerned with what values make our value expression under the radical negative. So our domain would be from negative 1 to infinity. So in part A, we want to find f of g of x. So we start with our f of x function, which is 2 to the x. So now everywhere I have an x in that function, I'm going to replace it with the g of x function. So it's 2 raised to the square root of x plus 1. Now if I'm looking for the domain of this composition, first I have to look at the domain of my inside function, which is g of x. The domain of that is negative 1 to infinity. And I also have to look at the domain of my new function. Okay? We have an exponent where we can have negative or positive numbers in the exponent, but since we have this radical, we still cannot include negative values underneath the radical. So our domain for that would be negative 1 to infinity as well. So where those two intervals, those two domains overlap, well, they're the same. So our domain for this whole composition is negative 1 to infinity. In part B, we want to find g of f of x. So we're starting with our g of x function, the square root of x plus 1. Everywhere I have an x, we're going to replace that with the f of x function. So we have the square root of 2 to the x, and then plus 1 at the end. Now we want to look at the domain. First, we have to look at the domain of f of x, which is negative infinity to infinity. Then we have to look at the domain for our entire new composition. Okay, so we said the domain of f of x was negative infinity to infinity. If we look at the domain of this whole expression, well, we have a radical, so we have to be concerned with any values that are going to make the expression below or underneath our radical negative. Well, no matter what value we put in for x, any number, if it's positive, raised to an exponent, whether that number is negative or positive, is going to be positive. So we have a positive number plus a positive number. So no matter what we put in for x, this radical, this expression, is going to be positive. So our domain for this composition is going to be negative infinity to infinity. This next example, we just want to look at the domain of compositions. So if we have f of x equals x squared minus 1 and g of x equals the square root of x, if we're looking at the composite function f of g of x, that will be equal to, we're starting with our f of x function. When we have an x, we're replacing it with our g of x function. So we have the square root of x, quantity squared, minus 1, which we could simplify down to x minus 1. Okay? The reason we might leave it in this form to start out is because when we look at our domain, it's going to be easier to see what our domain is. Okay? So, to find the domain of this function, we have to look at the domain of g of x, which is going to be any number greater or equal to 0. So we're starting at 0, going to infinity. Then we would look at the domain of our end result, the composition. Well, this is just x minus 1. It's a polynomial. So the domain would be negative infinity to infinity. Where those two domains overlap, we have to take all the restrictions. So the domain for this overall composition is going to be from 0 included to infinity. Now we want to find g of f of x. So we start with our g of x function. The square root of everywhere we have an x, we're going to replace it with our f of x function. So we have the square root of x squared minus 1. And now we want to find the domain of this function. So first we got to look at the domain of f of x, which is a polynomial. We know the domain of any polynomial is all real numbers, negative infinity to infinity. And then we have to look at the domain of our composition, so the square root of x squared minus 1. So since we have a radical with an even index, we have to be concerned with what values make this expression underneath the radical negative. So we have x squared minus 1. We want to make sure that is greater than or equal to 0. We solve, we get x squared is greater than or equal to 1. So thinking about this logically, we're looking for any x value that when we square it has to be less than 1 because we can't include that in the domain. The only x values that will make this x squared less than 1 is going to be a proper fraction. So a fraction where the numerator is less than the denominator. So we have to exclude from our domain any value negative 1 to 1. Because if we put any of these values in for x, it's going to give us a value that's less than 1, which if we put into here is going to make this expression negative. Okay, so now we have the domain of f of x, and we know what the domain of our composition is. We have to find out where those overlap. So we're starting with negative infinity. We go to a value of negative 1. We can include negative 1 in the domain. Now we have a union, and we have to start with a value of 1 and go to infinity. Okay, our domain here, going from negative infinity to negative 1 included, union 1 included to infinity, this means we're excluding any value between negative 1 and 1. Because as we discussed over here, if we put any of those x values in here and square them and then subtract 1, that expression underneath the radical will be negative. So we took the domain of f of x, which was all real numbers, then we found the domain of our whole composition. We found out where those intersections were of those domains, which is going to be what we have down below. Now we want to work in the opposite order. We want to decompose a function. So we want to find f and g such that h of x is equal to f of g of x. So we're told that h of x is equal to the square root of x squared plus 5. So now we're looking for f of x, and we're looking for g of x. Okay, g of x is our inside function. I think in this case it's actually easier to find what that function is going to be. So we're looking at what expression could be on the inside of this function. Well, we have a radical. If we take what's underneath the radical and rewrite that as a function itself, so g of x is equal to x squared plus 5. Okay, that's our inside function. Now we have to look and find a value for the expression for f of x, which would be our outside function, which is going to be the square root of x. So now think about this logically. If we are looking for f of g of x, we're starting with our f of x function, which is the square root of x. Everywhere we have an x, we're going to replace that with our g of x function. So we would get the square root of x squared plus 5, just working in the reverse order. Another example of decomposing a function, we have h of x is equal to f of g of x, which is equal to the quantity x plus 1 squared minus 3 times the quantity x plus 1 plus 4. So we're looking for f of x and g of x. First, let's start with looking for the inside function g of x. If we look at the polynomial we have for h of x, we have x plus 1 and x plus 1 in common. Okay, so we can start there and try to use that for our inside function. So g of x is going to be equal to x plus 1. Now if we replaced x plus 1 in our f of x function, that means this would be, in our original function, just an x. So we would have an x squared minus, this in our original would have been just an expression of x minus 3 times x plus 4. Going back through this, taking the composition, if we're starting with our f of x function, everywhere we have an x, we're replacing that with the g of x function. So we would get x plus 1 quantity squared, which we have up here, minus 3 times x plus 1, and then plus 4 at the end. Okay, so this is called decomposing a function, working in the reverse order to find out what the inside function would be and the outside function for our composition. Last part of this lesson is just going to discuss implicitly defined functions. Okay, so the general term for a set of ordered pairs x and y is a relation. If the relation happens to relate a single value of y to each value of x, then the relation is also a function. Okay, it would pass if we plotted those points where they meet that condition. We could use the vertical line test to show that that relation is a function. When we have cases of circles and ellipses, okay, so in the case of x squared plus y squared equal to 4, this represents a circle if we graphed it. That is not a function because it would not satisfy the vertical line test. Okay, for each x value, we would have 2 y values that would make that equation true. So what we can do is split this into 2 equations that do define the function. Okay, so if we would isolate y by itself, we would get y equals the positive of square root of 4 minus x squared, and y equals the negative of the square root of 4 minus x squared. Now we would be able to use your graphing calculators, graph each of these portions individually, and looking at the graph as a whole, we would see the graph of the circle. Okay, so that's called implicitly defined functions. We'll work more with those in calculus, those of you that decide to take that. Main thing you need to focus on in this lesson is the sum, difference, product, and quotient, being able to find all of those given f and g, and also being able to find the domains for each of those. Also, you need to be able to find the composition of functions f of g of x, g of f of x, and be able to find the domains of the composition, as well as being able to decompose a composition.